Hello, everyone. Welcome back to this new appointment of our 40 Under 40 e-lecture series on combustion. Today, we have the pleasure of having Dr. Preethi Rajendram Soundararajan. She's a lecturer in the Department of Aeronautics and Astronautics at the University of Southampton in the UK. Before joining Southampton, she worked as a postdoctoral researcher in the engineering department at the University of Cambridge, where she focused on studying hydrogen and plasma-assisted combustion. She completed her PhD at the M2C laboratory at Central Supélec, CNRS in France, specializing in thermoacoustic instabilities. She has been a recipient of prestigious awards, including the Amelia Earhart Fellowship, Marie Curie Fellowship, and the ASME Turbo Early Career Engineering Award. Preethi, it's a pleasure to have you here, and yeah, I leave you the virtual floor.
Thanks a lot, Salvatore. So hello, everyone. Good afternoon. Thanks a lot for coming to this talk, which is part of the 40 Under 40 lecture series. So today I'm going to be talking on a topic that is of much interest to the combustion community, which is on decarbonization, mainly focusing on the use of hydrogen and plasma to achieve it. So before I begin, I want to express my gratitude to the Belgian section of the Combustion Institute for organizing this really great seminar series that gives the opportunity for young researchers to showcase their work. In particular, I would like to thank Professor Parante, Dr. Iavarone, and Professor Dupap on inviting me to be a part of the series. While techniques that are developed towards decarbonizing combustion are widely applicable in several areas, just for the context, I'm going to briefly focus on the aviation sector, which is regarded as one of the most difficult sectors to decarbonize. So it's not a news to this audience that we burn hydrocarbon fuels with air, and this results in the formation of carbon dioxide, water vapor, and oxides of nitrogen, which are all pollutants. If we put some numbers on the effect of these pollutants on the environment, aviation alone contributes to 2% of global CO2 emissions. And if we include non-CO2 emissions, the impact of aviation on climate change is about 5%. The main point to remember here is that the emission is happening at a very high altitude, which makes it difficult to adopt any control measures after they are released. So this makes it important to develop techniques that limit their production at source, which essentially means altering the way we burn. We can think of two strategies to reduce emissions. First, by using low or zero carbon fuels that limits or eliminates the production of CO2. Or secondly, improve the combustion efficiency of these engines so we can emit less. Let's first look at the first strategy, which is on using low carbon fuels. So what if we stop burning hydrocarbon fuel and instead just use hydrogen? That way, there are no carbon dioxide emissions. We still have oxides of nitrogen, which has to be dealt with, but at least carbon dioxide is eliminated. The good news is we don't have to learn to burn hydrogen because hydrogen gas is highly reactive. However, the first challenge due to its high reactivity is the propensity to flashback. So if we look at this comparison of flame speed in blue between hydrogen on the left and kerosene on the right, we can notice that at a particular equivalence ratio, the flame speed of hydrogen is nearly 7 times higher than that of kerosene. So it is not safe to operate hydrogen in a premixed configuration as it can cause flame flashback. It also burns at a slightly higher temperature, which might favor the emission of oxides of nitrogen. So the question is, how do we burn hydrogen in a controlled and safe way? So to prevent flame flashback, we need to operate hydrogen combustors in a partially premixed fashion. So one way to achieve quick and well-mixed reactants for hydrogen combustion is through a jet-in cross-flow injection. In this technique, we have a cross-flow of air and a high-velocity hydrogen jet is injected perpendicular to it. Since we are only mixing air and hydrogen at the region where it ignites, there is no possibility of flashback, so it is safer to operate. And further, because of the higher diffusivity and velocity of the hydrogen jet, there will be good mixing between air and the fuel. This technique, we can also burn lean, thereby reducing NOx emissions. To study this, at the University of Cambridge, we developed a canonical configuration of a jet and cross-flow injection technique. So And in the schematic that you can see here, air flows from the bottom and exits through the top. There are a series of 3 jets of hydrogen that are injected perpendicular to this airflow. In such a configuration, the critical parameter is the velocity of hydrogen jet compared to the velocity of airflow, and this parameter is called the momentum flux ratio. So good thing about having such a canonical configuration is we can do a systematic sweep of this critical parameter, which is the momentum flux ratio. So for example, for this study, we changed momentum flux ratio from 10 all the way to 7,800 to understand the flame behavior better. So this enabled us to study a wide range of flame dynamics that is associated with the jet and crossflow configuration. So for this study, we looked at 60 different momentum flux values, but today I'm only going to focus on one particular crossflow velocity, just 4.5 meter per second, and 3 different jet velocities ranging from 310 to 78 meter per second. So this is just to show an example of the rich flame dynamics that this configuration exhibits. So these combination of jet and crossflow velocity results in momentum flux ratio between 300 and 20. First, to visualize the jet, we use the Schlieren technique under non-reactive conditions. So for this kind of configuration, Schlieren is well known to be to provide qualitative information on the mixing between the jet and the crossflow. So in this figure, we can see the instantaneous Schlieren images. So each row corresponds to a particular value of momentum flux ratio. And as we move from the top to the bottom, we go down in momentum flux ratio. So each column corresponds to a different instant of the Schlieren images at a particular momentum flux ratio. The first information that we can obtain from the different Schlieren images is how well the jet has penetrated into the crossflow. For example, if we look at this yellow arrow, which marks the jet stem distance, and here jet stem distance is defined as the length of the straight portion of the jet before it bends and interacts with the crossflow. So we can see that this jet stem distance decreases as we decrease the momentum flux ratio. And at the lowest momentum flux ratio, it completely vanishes and the jet bends as soon as it enters the chamber. The other thing that we can notice at the highest momentum flux ratio here is along the jet stem, there is no diffusion of hydrogen into the crossflow on the windward side, but there is a minor diffusion of hydrogen on the leeward side. So the story is similar at the momentum flux ratio of 82. So no diffusion of hydrogen on the windward side, but a minor diffusion on the leeward side. Of course, the story is completely different at the lowest momentum flux ratio because there is no jet stem and the jet bends and it stays very close to the inner wall. Now we can also get a quantitative measure of how well the jet has penetrated into the crossflow with the help of this yellow vertical line. This line marks the maximum spatial penetration of the jet at the lowest momentum flux ratio of 20. So compared to the lowest J, at 82, the penetration depth increases by about 72%. And at the highest momentum flux ratio, the penetration depth is about 40% higher than the lowest J case. So from this, we can say that at the highest momentum flux ratio, even though the initial mixing along the jet stem is poor, subsequent mixing can be quite strong, and this can result in good flame stabilization. As we decrease the momentum flux ratio, the mixing is also expected to gradually decline, and at the lowest mixing can be expected at the lowest momentum flux ratio. And now let us look at how this difference in the flow field as well as the mixing at different momentum flux ratio affects the flame structure. So in the top row, we see the averaged OH star chemiluminescence intensity coming from the flames. And OH star chemiluminescence is widely considered as a flame front marker. As we move from left to right, we decrease the momentum flux ratio. In the bottom, we can also see the true color flame photographs. So from this, we can say that as we decrease the momentum flux ratio, the flame length increases. And if we look at the general structure of the flame, in all the 3 cases, the flame takes a U shape, which is closed at the windward side and open at the lee side. If we focus first on the highest momentum flux ratio case, in addition to this U shape, we can also see this bright spot close to the center. To understand the reason for this bright spot, we need to look at the side view of the three jets, which is shown in the bottom. In this view, the jets are behind one another. So what we are seeing is the chemiluminescence coming from all the three jets. So if we first look at the high-speed video at the highest momentum flux ratio, and we can see that there is a partial liftoff of the flame on the windward side, but the flame is marginally attached close to the tip on the leeward side. When we decrease the momentum flux ratio, there is still a minor pinch off that can be observed, but the flame remains mostly attached at the injection location. And at the lowest momentum flux ratio, the flame fully remains attached to the injection location. So this lift-off that we see at the highest momentum flux ratio and a marginal attachment on the leeward side is what is seen as this bright spot at the center of the image on the front view of the jets. So to understand the reason behind the different flame topology, we also carried out large AD simulations of the jet and cross-flow configurations. And these simulations were validated with cold flow Schlieren as well as flame chemiluminescence, and the CFD showed a good match with the experimental results. As a first step, let us look at the instantaneous velocity fields from the LES, showing the velocity streamlines as well as magnitude in different colors. So as we move from left to right, again, we'd go down in the momentum flux ratio. The colors along the jet in this picture might appear a bit oversaturated, but this is because of the normalization that is done here. So the normalization for velocity is not done with the maximum velocity, but with an arbitrary velocity. And the reason for this is because we are dealing with a velocity ranging from 300 meters per second to 2 orders of magnitudes lower to 4 meters per second. So we need to use some arbitrary value so that we can see the different colors on this graph. We can also notice this embossed surface on the velocity field on the rightmost image. And this is the isosurface of fuel at stoichiometry. So this isosurface is indicated by this arrow on this image. And the isosurface of fuel at stoichiometry can be considered as an indicator of how well the fuel has mixed with flame, how well the fuel has mixed with air. So this isosurface is only prominent at the lowest momentum flux ratio and is only barely visible at the other two cases. It can be noticed very close to the injection location, but along the jet, it is absent. So at the highest momentum flux ratio, we can see that close to the injection location, the jet velocity is really high. If we recall the Schlieren image, then along the jet stem, we noticed that there was no diffusion of hydrogen into the cross flow along the windward side. And this is what leads to the partial liftoff of the flame that we observed on the flame chemiluminescence. However, along the downstream of the jet, we can notice all these small scale velocity structures. And because of these velocity structures, we can expect, because this small scale velocity structures coupled with the larger penetration depth can result in rapid mixing downstream of the jet. So although the initial mixing is expected to be poor, due to rigorous and fast mixing downstream, no fuel is expected to be present at the further downstream of the chamber, and this can lead to the formation of a short and compact flame. Now, let us take a closer look at what's happening on the lee side. Here we can notice that the streamlines show a minor recirculation zone that exists here. And this is because close to the jet stem, because of the higher momentum of the jet essentially behaves like a bluff body without interacting with the cross flow. This effect, coupled with the wake vortices close to the wall, results in the formation of a low velocity recirculation zone, which might potentially trap hydrogen and air and also some free radicals from the nearby adjacent reaction zone. So for example, in the bottom, we see the contours, mole fraction contours of perhydroxyl radical, which plays a crucial role in the chain branching reaction of hydrogen combustion. So just above the injection location on the leeward side, we can see a strong presence of the HO2 radical that is trapped here. So from this, we can confirm that there is some trapping of free radicals in this location on the leeward side, which is what helps in marginally attaching the flame on the lee side close to the tip. So essentially, at the highest momentum flux ratio, the flame remains lifted on the windward side due to higher initial momentum of the jet, but attached on the lee side due to the formation of this low velocity recirculation zone. When the momentum flux is increased to 82, there is still a short region of high velocity region close to the jet, which might result in a minor lift-off tendency. But of course, this is not as prominent as the highest momentum flux ratio case. We can also notice this ripples downstream of the jet, and this is likely caused by horseshoe vortices wrapping the incoming jet. But so essentially these ripples are going to help mix the fuel and air well. But still, these structures are not as strong as in the highest momentum flux ratio case. The mixing is also expected to be comparatively smaller and less vigorous. At the lowest momentum flux ratio case, the magnitude of the jet close to the exit has a much lower magnitude close to the region close to the exit. So this results in good attachment of the flame to the injection location. We can also see this embossed isosurface that extends along the jet trajectory. So this indicates that the mixing at the lowest momentum flux ratio is slow and gradual. And this poor mixing with the absence of turbulent structures on the velocity field results in this long flame which is caused by gradual mixing along the jet trajectory. In short, what we have seen here is that a canonical jet in cross-flow configuration can exhibit rich flame dynamics when the momentum flux ratio is systematically varied, and this information can be used to guide in building partially premixed hydrogen configurations. Now let's move on to the second strategy of reducing emissions, which is by improving combustion efficiency. One of the ways to improve combustion efficiency is through plasma-assisted combustion. So if we apply a high-voltage electric pulse in an air and fuel stream, it can produce this small region of bright plasma, and this plasma can help in several ways. For example, it can break down the oxygen in air and also break down fuel molecules to produce radicals such as CH and OH before the flame zone. Further, it can also cause local heating of the gas stream and favorably alter the flow regime. All this can help stabilize combustion with lower quantities of fuels than a conventional system. This can also result in low emissions through complete combustion of fuel and air by producing free radicals prior to the combustion zone. So at the EM2C lab in France, we applied plasma on a swirl combustor that operates with liquid fuel. So this configuration has quite some practical relevance. So here we are going to see the video of a flame. So this flame initially flutters. And the moment when this plasma is turned on, the flame gets stabilized. On the right side, we look at the high-speed chemiluminescence images in the top without plasma and in the bottom with plasma. So as we can see, when we decrease the equivalence ratio without plasma, at an equivalence ratio of around 0.57, the flame begins to oscillate and it eventually blows out. However, when we turn on the plasma at this equivalence ratio, the flame stabilizes and we can go all the way to 0.51 when the flame eventually blows off. So with the use of these high voltage plasma discharges, we can extend the stability limits of a swirl spray flame. If we take a closer look at what happens to the flame close to the oscillations, initially the flame oscillates, but at the moment the plasma is turned on, it gets stabilized. To put some numbers on how advantageous the plasma can be, on the right, we see the probability of blowout with plasma in red and then without plasma in gray. We see that the plasma lowers the probability of blowout to a lower equivalence ratio. And if we look at the frequency of oscillations in red for plasma and in black for black without plasma, we can see that the plasma delays the onset of oscillations to a lower equivalence ratio. In summary, what we can see here is that with plasma discharge, the probability of lean extinction can be lowered with swirl flames. And the plasma does this by delaying the onset of flame oscillations and anchoring the flame at the end of the oscillations. So these effects combined together can contribute to extending the lean blowout of these flames. Okay, so we saw that we can extend the stability limits of a swirl stabilized flame with plasma discharges. So the next natural question is, can we eliminate the use of conventional flame stabilizers such as bluff body or swirl, which imposes a pressure drop to the flow, and instead stabilize the flame solely with these plasma discharges? To answer this question, we developed a canonical configuration at the University of Cambridge that consists of a square cross-section channel, and air is pre-mixed with fuel and enters through the square channel. In the chamber, two sets of tungsten electrodes are placed, between which high voltage electric pulses are applied, and this results in the formation of a repetitively produced plasma discharges. From the schematic, it can be seen that in this combustor, there is no other stabilizer like bluff body or swirler to hold the flame. There are only these tungsten electrodes in the chamber that produces plasma discharges. So now if we look at the video of the experiments, what we can see here is the bright spot, which is the plasma discharge, and a blue flame stabilized on top of it. So as we can see in the chamber, there are no stabilizers. So this is quite novel because most of the studies in this area uses plasma to extend lean blowout limits, like what we saw earlier with the swirl flames. But in this work, we have achieved flame stabilization only with these discharges. So to understand the mechanism by which these flames are stabilized with plasma, we can look at these high-speed chemiluminescence images. So firstly, when the plasma discharge comes in contact with the fuel-air mixture, it ignites the mixture surrounding it and produces a flame kernel. So this kernel moves downstream and it is because of the bulk flow that is present. As the plasma discharges are repetitively produced, successive kernels are formed at the repetition frequency of the plasma. And as we keep increasing the repetition frequency, these kernels are produced more rapidly. So at a critical point, when the repetition frequency is higher than the bulk flow time scale, the kernels can merge with one another to form a continuous flame sheet. So this is the stable flame that is stabilized solely with the plasma discharges. Essentially, there are three possible regimes in a plasma stabilized flame. In the first, we have a stable flame where the kernels merge with one another to form a continuous flame sheet. Second, where the kernels are repetitively produced but cannot merge with one another due to higher bulk flow velocity. And the third, in which kernels are extinguished as and when they are formed. So based on this classification, we can determine the blowout limits of plasma stabilized flames at different repetition frequencies. So here we see a graph that shows the evolution of extinction equivalence ratio at different bulk flow velocities. So the markers show the lowest equivalence ratio at which we can have a plasma stabilized flame at a particular bulk velocity. The blue symbols correspond to a plasma repetition frequency of 5 kilohertz, and the red symbols correspond to a repetition frequency of 10 kilohertz. So as we can see, the extinction equivalence ratio is higher at 10 kilohertz, higher at 5 kilohertz compared to 10 kilohertz. And this indicates that when we increase the repetition frequency, we can stabilize flames at a leaner condition. So does this mean we can stabilize the flame at lower and lower equivalence ratio as the repetition frequency is increased? The answer is actually no. So what we see here is the same plot, but with other repetition frequencies at 15, 20, and 30 kilohertz. So we can see that the evolution of the extinction equivalence ratio at higher frequencies overlap with that of 10 kilohertz. So there is this difference between 5 and 10 kilohertz, but beyond 10 kilohertz, there is no difference. This means that there is a critical frequency that exists, which in this case is 10 kilohertz, beyond which any increase in repetition frequency does not affect flame stabilization. The reason for this is because the mechanism of flame stabilization is primarily through merging of flame kernels. For example, as we move from 5 to 10 kilohertz, this particular case, we make the kernels merge with one another, and thus an increase in repetition frequency contributes to flame stabilization. However, as we increase the repetition frequency to 15 kilohertz, the flame kernels still remain merged, and this increase in frequency does not particularly contribute to the formation of a stable flame. So in addition, we also carried out an experiment to compare the lean stability limits of these plasma stabilized flames with that of a conventional bluff body stabilized flame. So here on the left, we see the schematic that we already saw for the plasma stabilized configuration. In the chamber, we only have these tiny tungsten electrodes, so the flow blockage is quite negligible. But on the right side, we see a V-gutter bluff body configuration that presents a 45-degree angle to the incoming bulk flow. And this V-gutter configuration results in a flow blockage of about 40%. On the image here, we see the extinction equivalence ratio on the y-axis and bulk velocity on the x-axis. The black stars on this curve corresponds to the extinction limits of bluff body flames, and the colored diamonds correspond to a plasma stabilized flame. So what we can see here, at certain operating conditions, plasma can be as effective as bluff body in stabilizing flames. From the experimental results, we also developed a correlation based on Karlovitz stretch factor, which can help us predict the stabilization limits of these plasma stabilized flames at other operating conditions and fuels. In short, what this shows is that we now have a new way of stabilizing flames solely with plasma discharges, thus eliminating the need for conventional stabilizers. Okay, so we have looked at both ways of reducing emission, first by using low carbon fuels, then by improving the combustion efficiency. So essentially, we have brought in some changes to the flame in the form of fuel or the kind of injection or the way in which the flames are stabilized. So when we make any change to the flame topology, sometimes we may end up encountering certain undesirable instabilities in the flame. And one such instability is the phenomenon of thermoacoustic instability. Let us take the case of the jet and crossflow hydrogen flames that we looked at earlier. So at certain operating conditions, these flames become unstable, resulting in transverse flame oscillations. So if we closely look at these white circles on the video, we can notice that the central flame alternatively touches the left and the right flame close to the tip. This results in the shedding of flame pockets alternatively, which is not good because essentially the flame becomes unpredictable. This is happening because the flame has coupled with the acoustics of the air injection tube due to the phenomenon known as thermoacoustic instabilities. So this brings us to the third part of the talk, which is on tackling adverse effects due to thermoacoustic instabilities. In a broad sense, these instabilities occur because flame emits sound, and when we confine this flame in a chamber, which is typically the case in engines, these sound waves can get reflected back and forth. When this frequency matches with the resonant frequency of the chamber, then there can be very strong pressure oscillations, which will in turn affect the flow of fuel and air. The flame gets affected, the noise gets affected, and this keeps happening in loop. So I'm going to show the video of a lab scale combustor here that undergoes these instabilities. There is, of course, this intense sound that is emitted by this combustor due to these instabilities. But what we can also notice is that some of the flames blow out because of this phenomenon. So if we consider real engines, they have very high power density in the order of gigawatts, and even 1%, a very small fraction of this energy, of this thermal energy, is sufficient to drive really strong pressure pulsations. So because of these instabilities, we can have several undesirable consequences. Of course, the intense noise that we just heard, the blow off, and sometimes it can even cause mechanical failure. So for example, in this picture here, we can see a rocket motor that is completely torn off because of the thermoacoustic instability. These instabilities principally happen due to different time delays involved in the combustion process. For example, there is a time delay associated with the convection of fuel and air. There is a time delay associated with mixing, and as well as with the chemical conversion itself. If you use liquid fuels, then there are additional time delays due to atomization and vaporization of fuel droplets. If these time delays are sufficiently large, it can lead to unstable operation. Even if we use the same injector in a particular configuration, then with hydrogen, we are going to change the delays simply because it is a different fuel, right? So this can lead to thermoacoustic instability being triggered at operating conditions that were traditionally thought to be stable when operating with kerosene. So here is one such example from the same combustor at the EM2C lab in France. On the left side, we see a flame that is formed by a liquid fuel. And on the right, we see the same injector operating with hydrogen, and which results in a modified flame topology. So it's clear that when we change the fuel, the flame shape changes, the intensity distribution also changes, which may result in triggering of these instabilities. So it is important to understand these instabilities to develop control techniques and prediction tools that can be used as we transition towards low carbon fuels with newer technologies. So we studied the self-sustained oscillations on the annular combustor, namely MICA, at the EM2C lab in France. So it is important to study these instabilities in annular configurations because real configurations have an annular geometry. So I'm recollecting the feedback loop here again that happens between combustion and acoustics, which leads to strong self-sustained oscillations. So in this, here we can see a picture of MICA, which has 16 swirling injectors. The combustor can typically be operated with a lot of different fuels, and for this study, we focused on gaseous premixed propane as well as liquid heptane and dodecane that are delivered as spray in the chamber through a pressure atomizer. Of course, these are still hydrocarbon fuels, but the insights that we gather from with these fuels would be directly relevant to other low carbon fuels such as hydrogen and sustainable aviation fuels. So what we see here is the stability map of this MICA annular combustor at different thermal power and equivalence ratio. On the left, we have the premixed propane. In the middle, we have the liquid heptane, which is a volatile fuel. On the right, we have liquid dodecane, which has properties very close to that of kerosene. If we look at the stability map for the case of propane, we see that with propane, this combustor is unstable at most of the operating conditions. So these colors show the amplitude of instability. As we move from blue to green to yellow to red, we go up in the amplitude of instability. So at propane, we barely see any blue regions. So it is nearly fully unstable at all the operating conditions in this combustor. If we change to heptane, then we can start to see some blue regions, but these are still quite rare. The operating conditions at which stable operation occurs is still quite rare. And a heptane exhibits wide instability bands, and the highest amplitude of instability also occurs with heptane. As we move to dodecane, we see a lot of blue regions now. So the combustor is stable at a vast majority of points. The instability bands are also narrower, and the high amplitude regions are quite narrow as well. So from this, it is clear that when we change the fuel, the instability behavior changes completely. So this makes it important to understand and develop control techniques before the design stage of low carbon combustors. If we look at the flame topology in each case, we can see that with propane, the flame takes a shape of a full M. With heptane and dodecane, we see a hollow M. Essentially, the central luminous region that we see with propane is nearly absent with heptane and completely absent with dodecane. So the flame topology is changing, but how does it manifest as a change in the instability behavior? So to do this, what we can do is we can externally modulate a stable flame and measure its response. So on the left, what we see here is the feedback loop that we know from before, which caused the self-sustained oscillations in MICA. Now we want to decouple this loop and minimize the combustion acoustics interaction to a level where this feedback loop doesn't exist anymore, so that the flame is fully stable. So once we have a stable flame, we can modulate this flame externally by using loudspeakers, for example, and see how the flame responds to acoustic perturbations of different amplitude and frequency. Essentially, what we can do is we can do some kind of a sensitivity study with respect to acoustic frequencies and amplitude to understand what are the critical frequencies that we need to avoid in our combustor. The idea behind this is to represent the flame response in terms of a black box describing function that relates an input, which is the flow perturbations, to an output, which is the heat release rate perturbation. To do this external modulation, we used a single injector combustor, which is representative of the annular combustor. Now, our black box describing function will have heat release rate modulations in the numerator, which is the output, and velocity modulations in the denominator, which is the input. So this describing function has a gain and a phase, and it is a complex quantity. So for the three fuels, we carried out experiments to measure the flame describing function, which is shown by these figures on the right. The top row corresponds to propane, the middle row corresponds to heptane, and the bottom row corresponds to dodecane. So the describing function is a complex quantity. It can be split into a gain and a phase. These gain values are shown at different pulsation frequencies, which is marked on the x-axis. the colors show the different amplitude of input velocity fluctuations. So as we can see on this gain curve, for the same frequency, we can have different values of gains depending on the velocity fluctuation level. So the flames exhibit nonlinear behavior. On the phase curves, we can see that the slope is different with different fuels. So with propane, the slope is smaller, so we can expect a lower time lag. And with liquid fuels, the slope is higher, so the time lag is also expected to be higher. So once we have information on how flame responds to different input fluctuations, we can use this information in a low order modeling framework to represent the flame. So this model can then be used to predict when an instability will happen in the annular combustor. So based on the Rayleigh criterion that gives the condition for instability, and combining this with a describing function and injector impedance, we can come up with these bands of instability. So what this bands of instability states is that if the phase between our velocity fluctuations and heat release rate fluctuations is within this band, then our annular combustor is likely going to be unstable. So for example, here we see a sample phase evolution with these bands marked as a gray box. So if this blue phase curve lies within this gray band, then we can expect the oscillations to grow, resulting in an unstable behavior for the combustor. However, if the blue phase curve lies outside this gray band, then the oscillations are going to die out and we will have a stable operation of our combustor. Now let us see how this model predicts the instability behavior of our mica annular combustor with different fuels. So we have the instability band marked as a gray box here. We also see the phase evolution for three fuels. We see propane in red, heptane in blue, and dodecane in green. We know that the natural frequency of this annular combustor is around 750 Hertz. So this is the frequency around which we expect our combustor to be unstable. So this is marked by this black vertical line. So according to the model, the phase curves for propane and heptane lies within this instability band. So with these two fuels, we expect our annular combustor to be unstable. But for the case of dodecane, at this frequency, the phase curve lies outside this band. So this must result in a stable operation. Now, to confirm this prediction, let us go back to the stability map of our annular combustor. So on this stability map, now there is a black dot, and this is the operating condition at which these describing function measurements were carried out. So if we look at the propane and heptane case, these dots lie within the red region, which corresponds to the highest amplitude of instability. So like the model predicted, our annular combustor is unstable with propane and heptane. If we look at the case of dodecane, then this black dot lies in the blue region, which corresponds to a stable operation. So again, based on the model, whatever we predicted is actually true in the annular combustor. So of course, I only spoke about the phase of the describing function, but the gain also plays an important role. So essentially, we can write down a dispersion relation and represent the flame in terms of a describing function in this dispersion relation. When we solve for this dispersion relation, the phase of the FDF will correspond to telling us whether the combustor will be stable or unstable at a particular frequency, and the gain will give information on the amplitude of instability. So we previously saw that when we changed the flame topology, we changed the instability behavior. Now the question is, can we use this information to our advantage and tailor the injection in such a way that we suitably modify the time delays to make our combustor stable? For example, here we see three different spray profiles. So in the top one, at the exit of the injector, the spray is nearly uniformly distributed along the radius. In the middle one, there is some spray droplets close to the center. And in the lowermost one, there is no droplet present at the center of the injector. So of course, when we have this variation in the spray profile, we expect the flame topology to be different as well, and that's what we see. So because the flame topology is different, we are going to have a different describing function. So I have also marked these gray bands, which are the instability bands that we previously saw, and we also see the gain and phase revolution for all the three cases. So if we look at the topmost case, what we notice is that the phase curves lie within the instability band only for a selected frequency range. So between 550 Hertz to 800 Hertz. The gain is also more or less lower and remains constant. And as we move to the second spray profile, we now increase the range of the instability frequencies, and the gain also increases. And at the lowermost case, we have a very wide range of frequencies at which the combustor can be unstable, and the gain is also quite high. So essentially, the topmost flame configuration corresponds, we can expect that flame to be stable at a lot of frequencies, and the bottommost one will be the most unstable combustor for the range of frequencies considered. In essence, this work shows that we can tweak the fuel injection to our benefit and that way derive instability control techniques. So this brings us to the end of this talk, and I would like to quickly summarize some key takeaways for you to think about later. So we first looked at the case of a jet and crossflow configuration that exhibits different flame dynamics depending on the momentum flux ratio value. We saw that at the highest momentum flux ratio, the initial mixing was poor, but then because of a lot of small scale turbulent structures downstream of the jet, the mixing was quite intense. We also noticed that there was a recirculation zone on the leeward side, which helped trapping of free radicals that resulted in a marginal flame stabilization on the leeward side. At the lower J value, these turbulent structures were absent, so the mixing was also reduced. There was gradual mixing that happened along the jet trajectory, which resulted in a long flame. Also, this is the condition which led to the triggering of thermoacoustic instabilities, which resulted in transverse flame fluctuations. So ideally, what we want is a configuration that is in between the two, which can cause good mixing, leading to a stable flame while avoiding these undesirable thermoacoustic instabilities. Then we looked at the case of plasma-assisted combustion and how it can help extend the lean blowout limits of a swirl combustor operating with liquid fuel. So plasma can help in stabilizing flame oscillations that occur close to blowout. Due to plasma, the onset of flame oscillation was delayed, leading to a lower probability of extinction. We also further extended this idea of plasma-assisted combustion and developed a new method of plasma-stabilized combustion. We saw that each plasma discharge produced by a flame kernel can merge with one another when the repetition frequency is high enough, and this results in the formation of a continuous and stable flame sheet. These class of flames can have stability limits as good as that of a conventional bluff body configuration. So this can be used as a replacement for traditional stabilizers that impose a pressure drop to the flow. We also saw that when we bring some modification to the flame in terms of changing the fuel or the stabilization method, it can inadvertently lead to thermoacoustic instabilities. So when we compared a gaseous hydrocarbon fuel with that of two liquid hydrocarbon fuels with varying volatility, we saw that the instability boundaries and frequencies were altered due to a change in flame topology. We derived a model based on flame response to external acoustic modulations, and this model successfully predicted the instability behavior of the annular combustor. So this model can be used when designing combustors that will operate with low carbon fuels. We also saw that the change in flame topology and time delay can be used to our advantage by tailoring the injection location and thereby help develop stable combustor configurations. That's the end of the talk. Thanks a lot for coming to this talk. Thank you.
Thank you, Preeti. Thank you very much for your nice presentation. We have time for questions. So if anyone from the audience would like to ask a question, please unmute yourself or raise your hand and feel free to ask questions to our speaker. I see no questions yet, so I will just try to break the ice. And I have a curiosity, actually a couple of curiosity. First one is what would be the stability map of hydrogen in the same configuration? So you tried propane, dot again. Did you study that, or do you expect? How would you expect the stability map of hydrogen to be in those conditions?
We expect it to be certainly different because that's what we saw. So I didn't do the hydrogen work at EM2C, but it's currently being done by Nicola Weiss, who is in the audience, and I'm quite sure that it's going to change with hydrogen, not just with the fuel, but also with the kind of injector that the kind of swirler that will be used.
Okay. And if I may ask, just another curiosity that I have, what was the combustion model that you use in Star CCM Plus for your hydrogen in cross-flow configuration?
Yeah, so it was based on a laminar flow concept. So it was done using Star CCM Plus, so by one of our colleagues at Siemens. It did show when we compared the experiments and the simulations, it reasonably matches the Schlieren and the OH star chemiluminescence. So I think it produces a very trustable result.
Okay, so the validation was done on the images and on the Schlieren and the chemiluminescence images.
Yeah, it's still rather qualitative, but the qualitative matching was quite good.
Okay. Well, if there are no questions from the audience, then I'll take the chance to ask you another question regarding the energy of the plasma. Okay, Nicola has a question, please. Nicola, go ahead.
Yes, thank you, Preethi, for this very nice talk. I would have a question regarding the plasma work that you presented.
Yeah.
So when the pockets are ignited and they merge, so a flame can be stabilized, how did you ensure that the electrodes were not acting as bluff bodies? So how did you measure the temperature on the electrodes, or did you have a special visualization device to see if there is no bluff body stabilization?
Yeah, so we did have some conditions where the flames actually stabilized on the, let me just go back to this video. Yeah, so we did have some cases when the bulk flow velocity was quite low. Instead of the flames being plasma stabilized, it actually stabilized on the rod. So we had to check at each condition whether the flame is, it can be seen visually because the flame structure is completely different. So if we look at this video, then the flame is essentially produced as kernels and stabilizes on top of the plasma. Whereas if it is rod stabilized on the electrodes, then it occupies the entire region in the chamber. So we determined this visually, and we only considered the bulk flow velocities where the flame was fully plasma stabilized.
Okay, thank you. So do you have did you make a criterion based on a Reynolds number or a critical velocity where you have sure to have distinct stabilization mechanism?
We did not try that because all we wanted was avoid the rod stabilized configuration, only focus on the plasma stabilized configuration. But that could certainly be done because that depends mainly on the bulk flow velocity.
Okay, thank you.
Thank you, Nicola, for the question. Are there any questions from the audience? Oh, okay. Go ahead, Jean-Baptiste.
Thank you a lot, Preethi, for this very nice talk. I have a question concerning the plasma-assisted combustion system you have. It looks a lot like the wind tunnel from Tim Umbrello and Joe Lefkowitz studies, having two electrodes in the flow. And recently they published something about the parametric study with the flow velocity, and they went like up to 100 meters per second. Yeah. And they realized they have like elongation of the plasma. Have you tried going to such high speeds, and have you seen sometimes the elongation of the plasma in your work?
We do see that. We do see that when the velocity is really high. So, but then we did not consider, at least in the work that I currently presented, there was no, in particular, visually, the plasma was not stretched. But as we increased the velocity, we also did observe that there was quite a lot of stretching, especially in this configuration of the electrodes.
Okay. And up to starting at which speed?
It was not something that we were interested, so we didn't do a parametric study, but I mean it could still be studied. I mean, probably in the future we could try to look at it if it is of interest.
Yeah, it's a really nice configuration. Oh.
Yeah,
thank you.
It's quite canonical, so it's easy to vary the parameters. So it's
Thank you.
all my friends from EM2C that asked the question. I'm so happy to see them again.
I mean, it's their field of expertise. Okay, so if there are no more questions from the audience, I can we can thank the speaker again for a very nice presentation, and thank you again, Preethi, for accepting our invitation, for delivering this presentation. And thank you all for attending this seminar and for your questions. And yes, I wish you all a pleasant weekend, and I'll see you at the next appointment of our lecture series.
Thanks a lot. Bye-bye.
Bye. Bye, everyone.